Hi guys, this is the video presentation for SETK 2711 Section 02 Thermodynamics and Material Engineering Laboratory. Lab Report 7 Experiment 4 Vapor Compression Refrigeration Group 1. Date of submission is on the 5th January 2021. Date of experiment 29 December 2020. Our lecturer's name is Encik Khairuddin bin Ahmad. These are our group members: Muhammad Haris bin Abdul Hamid, Ahmad Aidil Hafiz bin Shaharuddin, Chok Shuzan, Nur Ikon binti Muhammad Ismail, and myself, Lakshana Kumari.
The introduction of this experiment consists of two parts. The first one is objective, the second one is theory. The objective for this experiment is to determine the coefficient of performance COP for the vapor compression cooling system. Next, theory. What is vapor compression refrigeration? From this diagram, we can know that the vapor compression refrigeration involves four main components, which are a compressor, a condenser, an expansion valve, and an evaporator. Firstly, the refrigerant enters the compressor as a vapor and it compresses to the condenser pressure. Then it leaves the compressor and enters the condenser. In the condenser, it cools down and condenses by rejecting the heat to the surrounding. After it leaves the condenser, it passes through an expansion valve where its pressure and temperature will drop drastically. The low-temperature refrigerant enters the evaporator and it evaporates by absorbing the heat from the refrigerator space. The cycle is repeated when the refrigerant vapor leaves the evaporator and enters the compressor. What is coefficient of performance, COPR? This COPR represents the efficiency of the vapor compression refrigeration cycle. From this diagram, we know that the heat is transferred from the low temperature space, which is cool tank, to the high temperature space, which is hot tank, and this process requires work, which is supplied to this system. Q2 in this diagram is known as QH, which is the amount of heat released from the cool tank, whereas the Q1 is known as QL, which is the amount of heat released to the hot tank. The formula of coefficient of performance COPR is desired output QL, which is amount of heat rejected from the cool space, over the required input, which is work in. Then we can use this equation, work in equals QH minus QL. Then we can find out the work in.
So the apparatus is refrigeration cycle demonstration unit R633 PA10 using R141B refrigerant fluid. Okay, next for methodology. So the issue study was that energy cannot be lost. So the heat taken in at low temperature must be dissipated into the atmosphere. So based on zero law of thermodynamics, without the aid of external agent, heat cannot move from a cold region to warm one. So in refrigerator, some energy input are needed to make the refrigerator work efficiently in order for the refrigerator to go into operation. Okay, so first some components were defined, such as condenser and evaporator. Next is a thermometer was observed for each location, and in order to continue record the readings, as shown in figure 1, we open the valve. Okay, to continue our procedure, water pipe was turned on and the water flow rate was set to 26 grams per second for the evaporator. And then set the maximum water flow rate for the condenser and switch on the main switch. Next, allow the cooling system to be stable for about 10 minutes after we had switched on the main switch and report some parameters. It took around 7 readings for one condition for the thermometer temperature reading. Change the flow rate of water to condenser from 26 grams per second to 10 grams per second. based on the data given, and we took about 10 minutes for one flow rate. Repeat experiments around 4 times. So at the end of the experiments, ensure that the system is closed in compliance with the protocol we referred to during the experiment. Then key switch will switch off, the pipes for the water supply will turn off, and lastly, as shown in figure 2, we close all the valves to the shutdown position.
Next, we move to the result. This is the data that we got from the experiment. From the data, we need to calculate the rate of heat transfer at the evaporator, rate of heat transfer at the condenser, and the coefficient of performance. This is how we calculate. First, the rate of heat transfer in the evaporator, which is QL equals to mass flow rate times by specific heat of water times by difference in temperature, which is T2 minus T1. The mass flow rate, we need to convert it into kilogram per second and the temperature into Kelvin. Second, the rate of heat transfer in the condenser, which is QH equals to mass flow rate times by specific heat of water times by the difference in temperature, which is T4 minus T3. Note that both QL and QH are defined as magnitude. Therefore, the values are positive. The coefficient of performance of refrigerator, which is COPR, equals to QL over QH minus QL. So, we need to calculate all the coefficient of performance using this formula for all tests.
Hello, my name is Muhammad Haris and I'm going to present for the discussion part. Okay, first of all, this is our graph at figure 1, temperature versus condenser flow rate graph. Okay, this is our result. We have seven temperatures here, temp 1 until temp 7. Okay, for the next figure 2, is compressor power input versus condenser flow rate graph. Okay, the blue one is our line based on the data given. Okay, based on the result in table 1, all data that we obtain is accurate but still have some errors. There may be numerical error in estimation the evaporator heat and the condenser heat rate transfer. Some of the mistake is time taken to run away for a few seconds, and maybe the position of the reader eyes not perpendicular to the scale of the thermometer, so we cannot collect the data accurately. Okay, now let's turn to our first question of discussion. Calculate the rate of heat transfer that occurs in evaporator and condenser or the past test run and discuss the result. For this result, we use the formula QL equals to mass flow rate multiplied by Cp multiplied by T2 minus T1. For the mass, we use 0.026 kg per S and Cp 4.187 kg per kg. For the test one, we get the value 0.03266 kilowatt, and the test 2 0.02177 kilowatt, test 3 0.2177 kilowatt, and the test 4 0.02177 kilowatt, and the test 5 0.02177 kilowatt. And for the value is we define as magnitude, and therefore it is a positive quantities. Okay, for the discussion, the rate of heat transfer at evaporator QL for test 1 is increased, but for the test 2 until test 5 is same and decreased. This is maybe because the value of temperature change from T2 until T5 is same. Okay, and due to some errors while taking the temperature value, like position of the reader not perpendicular to the scale of the thermometer, so the value is not accurate. Next, for the rate of heat transfer at condenser, we use the same formula, but the temperature change we take from T4 minus T3. Okay, for the value of rate of heat transfer at condenser for test 1 is 0.4246 kilowatt, and the test 2 0.277 kilowatt, and the Q3 and test 3 0.6330 kilowatt, and the test 4 0.4683 kilowatt, and the test 5 0.347 kilowatt. For this value, we also define as the magnitude, so the quantity is so they are positive quantities. For the discussion, the rate of heat transfer at condenser QH of test 1 and the test 2 is increased. You can see here. Then for the test 3 until the test 5 is decreased. This is maybe because the temperature change from the test 3 until test 5 is smaller than test 1 and test 3 and test 1 and test 2. And due to some difference of mass flow rate from T3 until T5. Okay, due to some same error mentioned in QL, like the ice of reader not perpendicular to the value of thermometer, so we cannot take the value accurately. For the value of coefficient of efficient of refrigerator COP, we use the formula QL per QH minus QL. For the test 1, we got the value for COP 0.08332, for the test 2 0.03084, for the test 3 0.03562, for the test 4 0.045868, and the test 5 0.06683. Okay, next question. Explain the effect of changing the condenser flow rate of T1 until T6 to compressor power. Draw the graph and discuss the result obtained. Okay, as you can see, this is our graph, temperature versus condenser flow rate. So based on the figure 1, all 5 tests, temperature versus condenser flow rate, temperature was influenced by the condenser flow rate, which means as the temperature increase of T1 until T7, and the condenser flow rate will be decreased. But except for the T5. At the T5, the temperature remains the same from the test 2 until test 5. This is maybe because the temperature data is not accurate due to some of the errors, experiment errors. Some of it is the parallax error when reading the thermometer is one of the errors at T5, T6, and T7. To solve the problem, the thermometer scale should be perpendicular to our eyes. In addition, the temperature at T1, T2, and T3, and T4 taken from the electronic thermometer shift over time, so the exact value cannot be taken. In order to pretend this, we can take the average value temperature. Okay, for the next graph is compressor power input versus condenser flow rate. Based on the figure 2, the graph shows the compressor power input versus the condenser flow rate from T1 until T7. The power input of compressor increase as the condenser flow rate increase and vice versa. Therefore, the compressor power is inversely proportional to the condenser flow rate. The power input value cannot be exact because they change over time. To solve the problem, we need to take 3 times the reading of power input and take the average reading of value for each case. Other mistakes that may be considered in this experiment are that the system may not be in good shape, like the pipe also does not connect correctly, so it will cause the joint to leak, and this would make the flow of water unstable. Make sure the joint properly and avoid leakage before beginning the experiment to avoid this issue. In addition, since it will influence the outcome, make sure there are no air bubbling in the tubing. Let the water flow for a few minutes before starting the process to solve this problem. Okay. For the graph, you can see here our blue line.
Now we move on to the conclusion. The coefficient of performance COP is directly proportional to the rate of heat transfer in the evaporator QL. We also can conclude that the condenser flow rate is directly proportional to the compression power. In addition, as the condenser flow rate increases, the work input increases. Furthermore, we can also summarize that the condenser flow rate are inversely proportional to the temperature T1 to T6. These are the references. There are 3 references that we referred to do the lab report. That is all for the video presentation. Thank you.